Okay, and we are recording. So take it away, Joe.
All right, welcome everyone to the second class of Introduction to Wooden Shipbuilding. Something we're trying out here is one of our digital courses. And there we go. So the boilerplate that goes out on all of our products. I'm Joe Lingaze. I'm the Director of Sales Training for the Flagship Niagara League. We have Chuck Johnson, the educator and volunteer coordinator for the Erie Maritime Museum, which is the physical space where the ships tie up. And feel free to get in touch with us if you have any questions, comments, concerns, criticisms, knock-knock jokes. And we're in week 2 of a planned 4-week session. The recordings of this are being posted on the Erie Maritime Museum YouTube channel. So the easiest way to find that is just to go to YouTube and put in quotes Erie Maritime Museum, and you should find it right off. And if this is a hit, we may do this again in the autumn, expanded, polished a little more. So let us know. Something I was remiss on the last one. I had citations for all the images on the slides that weren't my photos, and they were on the last slide, so they got cut off. So here, for the record, for the YouTube video, if anybody wants to track things down, here are the citations for the first slide, and the citations for the second slide. Most of it is just from Wikimedia Commons. So if you were to Google the noun in question, like HMS Victory, and the Wikimedia hit is what would come up. And for those who are joining us for the first time, or who like repetition, the course goals are to broadly understand how wooden ships developed in the Mediterranean and Atlantic worlds, from the very basic beginnings, which we talked about last week, into what I think probably many of you are more interested in, the apex of wooden sailing ship technology in the Great Age of Sail, when it is in effect a fully developed technology, and there's no more room for advancement until material technology comes in. We'll talk about throughout the course how the materials you're working with and the context in which you're building the vessel are going to really dictate a lot of the choices you make. There are inherent structural properties of wood, of metal, of concrete, of anything you want to build a ship out of. And you can build a ship out of anything. You can build it out of lead, you can build it out of candy canes, you can build it out of water if you freeze it. But every one of these materials has pros and cons. Some have more pros than cons. And the pros and cons of wooden construction are why through basically every culture in the world, you see that being the primary shipbuilding material until really until the Industrial Revolution. We're going to understand or talk about anyways some of the basic elements of constructing a wooden ship, and we'll be getting to that a little bit this week, talking about the pieces and parts and how they go together. And we'll be looking at interesting examples from archaeology. So basically stuff that I think is cool, from the history of going back as we did to prehistory last time, but mainly focusing on the last 3,000 years or so. And this should be the last review panel. What shapes a watercraft? It's an artifact. It's made by human hands, and so it carries with it elements of human culture, human aesthetics, human understanding or lack of understanding. It's a thing that's made. It's a combination of simpler tools and technologies. So the technologies that go into even a basic ship include things like rope, which is probably something we'll talk about at some point, but it's a pretty interesting technology. It's things like the inclined plane and other simple machines. A watercraft is the product of a certain combination of material technologies. So it's the ability to process and use wood, the ability, if you have it, to process and use metal. And whether you're making a wooden ship in the Stone Age or the Bronze Age or the Iron Age or the Modern Age, makes a huge difference. Every ship is designed more or less to do a certain thing, to address a problem, like getting fish from the middle of the ocean to the coast, or moving things up and down a river. And everything happens in a geographic context. So it's a windy location, windy climate, or a less windy climate. You have deep water, you have shallow water. It's warm, it's cold. All of these things combine to constrain and inform what a culture's watercraft look like. And we talked about 3 basic shipbuilding traditions. Shell first, where you build the skin of the vessel first, and then piece in the structural support, the frames. Frames first, where you build the skeleton first, the structural support, and add on the skin afterwards. And bottom first, where you build a foundation and then the sides up. Most ships you'll see are products of the first 2. And today we're primarily going to be talking about shell first or skin first, which is very old and still in use. And from last week, we'll remember our old friend, the Dugout Canoe. This, in most shipbuilding traditions, is the basis for wooden ship construction and design. You start by hollowing out a log so you can sit in it and paddle it, and then you start adding pieces, a little bit on the side here and there to keep the water out better. And from there, it's just a jump to putting more and more on, and eventually you've got the Starship Enterprise, just by process of addition and refinement. And the way I'd sort of like to enter this discussion about shell first technology and what informs the way a watercraft is shaped and designed is by starting with a comment or a question from last week. People were interested, or at least a person was interested, in the Hogging Truss on this ancient Egyptian ship. You can see there's a big rope over the heads of the gentleman rowing the ship, going from the front to the back. And what it's effectively doing is using the middle of the ship to hold the ends up. Now, why would you need this? There are a lot of reasons, and we'll get into that. And this Hogging Truss technology is something that you see into pretty much the modern age. So the Oneida here, this is a Great Lakes bulk carrier, converted packet boat bulk carrier, built in the 1860s, wrecked in my neighborhood just up the road here in the 1890s. It's in 5 feet of water, so you can go see it if you're into that kind of thing. But you'll see there's a bridge like structure on the side there, an arch going from near the bow to almost to more than halfway back, and that's a Hogging Truss, and that's the same technology. It's a structure that pulls up the bow and the stern of the ship by connecting them to the middle, just the same way a suspension bridge works. Hogging, I had a cat in reach I'd show you with one of them, but hogging is when the middle is supported more than the ends are. So this is one of my own illustrations. It's certainly high on the scale for artistic merit, I'm sure. But generally in ships, they're fatter in the middle and pointier at the ends. So typically what you have is the water is, relatively speaking, pushing up more in the fat middle, and it's supporting the skinnier ends of the vessel less. And this is more or less true for all vessels. And of course, gravity. You have various heavy things in the stern and bow often, usually just the structure of the ship, because that's where everything ties in together. That's being pushed down by gravity and not supported by the water as much. So the result, this is a photo of the Constellation in the 1990s before its major restoration. And I don't know if it jumps out at you, but it jumps out at me. It's kind of sagging off in the back. This is a ship that's hogging because it's fairly big, quite old, and everything is loosening up. The whole structure is easing down, and the extremities, the bow and the stern, are easing down more towards the water. Of course, the opposite of this is sagging. You see it less often. I've represented a fairly modern commercial hull ship at the top there, and the stress is involved at the bottom there. Sagging is when, for whatever reason, the middle gives out. Typically, you see this in overloading or habitual heavy loading, or in a situation where the ship breaks its back, either through weather or some structural deficiency. There were a number of Great Lake ships that were made of iron, not steel, that did this in the around the turn of the 20th century. But sagging is the opposite, and it's when the middle goes down, not the ends. So talk about some of the decisions you make, or the decisions that are made for you when you're building a ship. So a ship can be small or large. About the smallest wooden ship you can imagine is a Coracle, like the one on the left. This is, I believe, a representation of Stone Age Britain, Neolithic Britain. But coracles are something you see throughout the world. And basically, it's a wicker basket with some sort of skin around it, usually animal hide. And you make a one-person sized boat. On the large side, on the right, you have the HMS Victory, which is about as big as you can get. So in the neighborhood of 300 feet long, wood is at its structural limit. So it becomes increasingly unfeasible to build a ship and have it support its own weight effectively when it's bigger than 300 feet. Also in the rig, you're looking at crossed yards that are over 100 feet long. And that is also something where you're really running into diminishing returns in what you can do with a piece of timber and have it hold up its own weight. Another choice is whether a vessel is full or fine, which are the maritime terms for round and plump or not very round and plump. And both has pros and cons. So typically you'll see merchant vessels of all eras being fairly full because you're willing to trade a little speed, a little deftness, a little ability to make ground to the weather for a little more space. Also, a full vessel floats very well. An example of a very fine vessel would be just about any modern naval ship. They tend to be very, very narrow, very sharp, tend to cut through the water. And that's why if you're in the Navy and you go through a storm, you tend to get the worst of it because you're punching through the waves and they're ending up on deck. But like our old friend, the Santa Maria of Columbus, Ohio, is an example of a very full vessel. Basically as full as you can get, very bathtubby. And from last week, the solar barge of Corfu from the Great Pyramids is a fairly fine vessel. At least at the entry here, you can see it's very sharp and only slowly widens out towards the midships area. Another constraint or choice you have to make is the draft of a vessel. So generally, outside of context, more draft is better. The more of the ship you have under the water, the more stability you have. It's effectively the foundation of the vessel. However, in the real world, you often have to worry about where the bottom is. So in river situations, in situations like up here on the Great Lakes 200 years ago, where you don't have reliable charts of any kind, and you have a lot of shoals and rocks that might surprise you, it becomes desirable to have a relatively shallow draft. And so this is another choice or compromise you have to make in the design. Another way you can approach this is the ratio between the length and the beam of the vessel. So you can have a relatively wide ship or a relatively narrow ship. Again, this is a highly professional illustration done by myself, but the one on the left is roughly 3 to 1. You'll see that in things like river barges, something that's got to carry a lot of weight and doesn't have a lot of draft to do it on. So you can't make the ship deeper, you have to make it wider. 6 to 1 on the right hand, you seldom see anything like that on a wooden ship, but you will see it on wooden boats. Rowing craft, that sort of thing, small river craft. And generally, when we look at all wooden boats and ships through all of time, making some broad assertions here, the vast majority of vernacular craft, craft that everyday people are using, common craft, are between about 30 and 100 feet long, which would be roughly 10 to 30 meters long. Generally, you're going to see a lot of ships that have a full hull shape with ends that are to some degree or another more fine. Typically quite round and arched in the very middle and midships, and then to more or less degree coming to a point. So when we look at something like the Santa Maria, that point isn't very sharp. But when we look at something like the solar barge, you can see where it's definitely tapering at both ends. The length to draft ratio is generally going to be about 1 to 10. So if you've got a 100-foot vessel, typically it's going to draw at least 10 feet, but this will vary widely with context. And typically the length to breadth ratio is between 1 and 3 and 1 and 5, with around 1 and 4 being pretty common. So using these general specs, one of the things we're going to do in a future class is unfortunately not in real life, but in the sphere of our imagination, build a ship using context and some elements that as a sort of lab exercise. What are wooden ships made out of? Well, they're made out of wood. What kind of wood? The simplest answer is what kind do you have? Most types of wood, just about every type of wood, can be used for ship construction, but some are better than others, and some are better in certain contexts than others. So for structural members, the frame, the backbone, you're looking for typically a hardwood. And white oak is, in the Atlantic world tradition, the preferred hardwood for most of the period we're thinking about here. And on the right, you have a picture of an oak tree. If you've never looked at an oak tree, it has long lengths that are straight, but it's got a lot of craggy bits too. They tend to be gnarly and twisty and visually interesting, I guess. But you also have a lot of naturally curved pieces that can form parts of a ship that take a curve. So frames and braces and things like that. In modern replica shipbuilding, we use a lot of tropical hardwoods. So those are rainforest trees like Santa Maria and different types of mahogany because those are available. But generally, you're looking for something that's strong, dense, and rot resistant and grows in the appropriate length. For structural softwoods, there are a couple kinds of pine trees, spruce trees, fir trees that are preferred. But if you generally look at a conifer, like the Douglas fir in the picture here, you can see that most of the mass of the tree is in the central column. And these softwoods tend to be strong for their weight. So they're not quite as sturdy as something like oak, but pound for pound, they're very good for doing things like masts and yards. They get you there, and they come in long straight lengths. You can make a whole ship out of these if you're so inclined. Niagara is mostly conifers, pine and Douglas fir. So the frame, the planking, the decks, the spars. Softwoods tend to be a little less resistant to rot than your white oak or your preferred hardwoods, but still they get the job done. It's probably my finest illustration of the batch. The first step in building almost any wooden ship is to lay down a keel. And it's the ancestor, or its ancestor is the dugout canoe. But your typical keel is going to be a squared off length of hardwood like oak, just about as long as the ship you're building is going to be. So between 4/5 and 100% of the end result. And it's going to be square or oblong. The next step is going to be to add stem posts and stern posts of some sort or another. Again, a fine illustration, but you can see the stem post here arcs forward a little bit. It's common. The stern post is a little straighter. That's useful if you've gotten as far in shipbuilding as having a fixed rudder. So if you have a rudder that's built on all the time and aren't steering the vessel with an oar or a paddle, then it's convenient if the thing the rudder hangs on, stern post, is more or less straight up and down. So some rare pictures of Niagara outside her natural habitat. You can see pretty clearly behind our beloved executive director, the stem post and the keel structure in the bow of the ship here. And same in this picture, a little more clearly. Now, a lot of what you're seeing in the keel here is actually the ballast keel, which is a big chunk of lead that's fixed on to make the ship a little more stable. But that structural ridgeline that is the stem post going down and the keel going all the way back and the stern post or equivalent going up again in the stern is going to be the primary element of just about every wooden ship you'll ever see. And almost all of them incorporate a rabbet. Now, rabbet is not related to the word for bunny. It's from the Old French and is related to words like rebate and abatement, but a rabbet is a long continuous notch that travels the length of the keel and typically up the stem post and the stern post as well. So in the view you're seeing, you're looking down the length of the keel, or you can be looking straight down the stem post, for example. And what the rabbet is a mechanical joint which allows the planks to lock in to the keel structure. So you've got effectively a huge amount of surface contact between the members, locking them together, not just the fasteners. And the simplest way to build up a wooden ship, shell first, is to start with a keel, rabbet in your garboard planks, going all the way down, notch them in to the stem post and the stern post, and then build up the next layer. And those also get rabbeted in at the stem post and the stern post. This is the Draken Herald Fairhair, which I'm not going to attempt to say in the original language, but it's a replica of Viking ship. And this, I think, is a pretty good picture of a stem post rabbet in the wild. So looking at the joint between the vertical stem post, which has you can see a little bit of the dragon head on top. The planks are coming in and notching in to a groove that runs the length of that stem post. And today we're talking about shell first, skin first, which is a continual line through the history of shipbuilding from earliest times and still in use today. If you buy a fiberglass boat, it's effectively the same kind of technology as shell first, ancient Mediterranean, or the same approach to things. Frame first comes a little later. We start edging into it in the Middle Ages, and it becomes the standard for constructing big ships anyways, by the Great Age of Sail. But there are various ways that you can construct your shell first vessel. And largely it comes down to the elements you have on hand, the technology you have on hand. And the local materials. So last week we saw an example of a sewn boat on a large scale, the Khufu barge, where the planks are connected together by string, by rope or twine that is laying on top of a batten. And on the left-hand side, you can see in cross section, the line is going through the planks, and a photo from life of the reconstruction of that ship. You can see in the very foreground here how the planks are being bound together. This is a way of doing things that's not all that common, but persists today. You can also edge join a vessel's planks. This is fairly common, and basically it's pretty similar to the way a lot of your furniture is made. So if you're sitting at a table, the tabletop is probably put together in about this way, with some sort of mortise and tenon system. And typically in an edge joined plank first vessel, you'll have the planks joined directly together, and then the tenon will be fixed in place with some kind of fastener like a nail or a trundle. This is maybe not the best picture, I apologize for that, but it's a fairly modern example of your basic edge joint ship. This is the beginnings of a Chesapeake Bay bug eye, which is a fishing vessel that really shows its roots to dugout canoes. In fact, this is part of a general family of Chesapeake vessels called log canoes. But you have these big, barely worked down planks or logs, logs that are most of a tree, that are edge joined together and chunked up that way. And then as you come around the corner, the construction becomes a little finer. But you can see in the very foreground some of the cuts to tenon that into the next plank there. And a third, and probably the most common, probably the most the closest to most of our experience in shell first boat construction, is lap strake, which is where the strakes or planks overlap each other and are fastened directly to each other. Usually a metal fastener is involved. I can't think of any examples where this is done with wooden fasteners. I think the strength would be an issue. So typically you're seeing this done with some sort of nail or brad that's driven through and in some way peened over or bent over. So like the Draken is a typical 1,000 years ago-ish lap strake vessel on a fairly large scale. And you can see the individual metal fasteners lapping the planks together. This is Cutter 1 at the Erie Maritime Museum, one of Niagara's boats that we use as a push boat. It's also lap strake. So this is during the rebuild process, and you can see the overlapping planks, and you can see the little dabs of dark color, which are nails that are covered up with a little primer. But lap strake is something that's used, at least on small scale vessels, up to today. So once you've built up the skin of your vessel using one of those methods, and you're using planks that you're bending into place, typically the ones that go in at the keel, at the rabbet, or more or less flat and straight. And as you add, you can curve around and add a little more bend as you go. And that's facilitated by steaming or soaking or things like that. You come to the top, you put in your deck beams or some equivalent structure. And what that allows you to do is to complete the girder. So you have a structure that's fixed on 4 sides, not open to the top, and so is much more stable. And it's also allowing you to finesse the shape of the ship a little bit. So you can push the sides out, pull them in from spot to spot as you go using the deck beam installation. And generally the final step in constructing a skin first wooden ship, another fine illustration, is you're going to add in the floor timbers at the bottom. Those are relatively large structural timbers tying the sides together and reinforcing the foundation of the ship. You'll add your frames, which go up the side and tie the planks together. You'll typically add a clamp or a waterway, something like that, which is a timber that goes around the perimeter of the ship at the deck edge, either above or below, and ties it together there. And you'll add your various knees, which are, here's a small example, but just supports between the sides of the deck or what have you. And you can see all of this going on in examples like this. This is a partial replica of a 7th century CE Byzantine wreck from Yasiada, which is in Turkish waters. But this is an example of a late plank first construction ship when we're transitioning to frame first. You can see the deck beams going across, sticking out, which I think is a nice look, and tying the top of the vessel together. This is the stern section we're looking at, I believe. And you can see a little bit of a clamp underneath those deck beams. And this is just all tying the structure one part to another. All right, I'm going to invite Chuck back. I'm going to get a little fluid in me. And I think we probably went at that a little fast. So I expect we've got a fair amount of questions on that. I think you're on mute, Chuck. Okay, no help on the talking front, I guess. Okay, and the Q&A from Chris Finnegan. In made masts, would they use woods of different strengths, characteristics, mimicking the heartwood core and sapwood of a grown mast? Would those differences in material characteristics have any significance in mast making like they do in bow making? So typically, my understanding is in mast making, you want the end product to be as uniform as possible. And I think that unlike a bow, or I think of a guitar neck, which is another thing where compression is built in, a mast or a yard or another spar doesn't bend, doesn't compress always in the same direction. It needs to be able to go back and forth and absorb stress in a variety of different ways. So certainly in all the masts I've worked with on ships, you're going for uniformity. Keith Hovius, how do you get the bow to a point? Or do you just put the bowsprit out to the front? Let me look around in my pile of scraps of lumber that I've assembled. I'm much better at doing this in person, pointing at things and poking things than I am, talking to a dead screen. So I apologize, but and I'll lose the PowerPoint too. So my fingers here are the stem post, and we'll say it's got a rabbet on the side there. You get the bow to a point by putting a relatively flexible piece of wood into the rabbet and then horking it around. And you can do this. It's pretty remarkable the extent to which you can bend a 3-4 inch oak plank if you prepare it a little bit and really get the goon squat on it. But that's how you come to a point. And if you look at fairly early ships, a lot of them do come to a point. So roundness is something you see mostly in later, larger merchant vessels, and it's built in to provide buoyancy. A clamp is basically, it's a beam that goes around the perimeter of the ship, just under the deck. So on another odd bit of lumber here. So if this is a deck beam, a clamp is going around on both sides, and it's supporting the deck beams and tying them to the sides of the vessel. There are about 19 things in the chat, so maybe we look there. All right, Wyatt's saying live oak is great too. Yeah, basically white oak, common oak, the sort of generic shipbuilding oak of the great age of sail is European common oak, but white oak comes in a lot of different varieties. And locally here in Ohio, Pennsylvania, Michigan, bur oak, BURR oak, is really great. It's got kind of a knobbly substructure with whorls in it that makes it very strong, hard on tools. Live oak is very hard, very strong. I think it grows primarily in the South and Atlantic coasts of the U.S., but they're all good options. And local availability is mainly the thing. The illustrations, I can't put those up for purchase. Yeah, I don't have much talent, and I didn't try very hard for anything other than clarity. We'll put it that way. Where was the Brigade dry dock? Typically, Niagara hauls out at Great Lakes Shipyard in Cleveland, Ohio. They've got a travel lift, which is a ridiculous contraption, but it's a big sling on wheels. You just pull the ship in, the sling comes up, and it drives off and puts the ship down anywhere you want it to. A few more in the Q&A here. Just move some windows around. Regarding bluff versus sharp bows, how does that affect turning? Basically, if your ship is shaped like a bathtub, it'll maneuver like a bathtub. So it's difficult to come through stays into the wind to tack, because something that's like a wall running into the water on the front of your vessel is going to slow you down. But if you're running a square rigger on the trade winds, maybe that's not a big concern for you. And the nice thing about a fat, broad, bluff bow is that it won't rise to the water. So you don't punch through the waves and have them end up on deck as much as you sort of coast over everything. So pros and cons either way. Redwood. I have never seen or heard of redwood used as a shipbuilding timber, but I'm not from the West Coast where they're from. So I might be missing something. Am I going to work on the dry dock this fall? I might have been promoted out of that. I am one of the top 10 traditional caulkers in Erie, Pennsylvania. I'll tell you that. So if things get tight, I might get called up to the majors again. But hopefully my old joints are respected. I know over time there have been situations where American and British ships or French ships have taken on unique construction features. Is there an overall reason for that, building materials, specific need, or is it just the expertise developed differently by each country? Folks have different ways of doing things that are cultural. So I think that would be the latter thing. But largely, I'm going to make a blanket statement that may or may not be supportable. I think the differences are coming from the context and the materials at hand. So Americans develop ships with sharply raked masts like Niagara and Baltimore Clippers. That's the short reason for that is we had a lot of trees. We didn't have a lot of rope because rope is a manufactured industrial product that comes from a major metropolitan center, usually Europe, using materials that in the great age of sail are probably imported from somewhere else. So it's a thing that's made in a factory. We didn't have a lot of that, but lumber grows on trees. So with a raked mast vessel, you only really have to support it in one direction, because if it's falling backwards all the time because it's raked back, you don't have to stay it as much in that direction. And I think, in a lot of the differences you're gonna see in maritime shipbuilding traditions are going to be because of specific material or geographic constraints. Are there any bad interactions between varying hull materials? Mainly wondering about wood that are less well known than galvanic corrosion, nail sickness, etc. Yeah, galvanic corrosion, for those out there who aren't familiar with, is when you have a more noble or stable metal, and a less noble or less stable metal, and electrons travel from one to another, and the weaker one corrodes. So my 1978 Chevy Malibu came with aluminum wiring in the wiring harness because it was built in the copper crisis, and aluminum is far less noble than stainless steel. So every time the aluminum wiring lost the casing and touched the steel body or steel frame, it would corrode rapidly and turn to a fine white powder. And for those of us in the Rust Belt, you've certainly seen some sort of preferential corrosion like that out in the wild. And that's a big issue on metal ships, and an issue less so, but still an issue on wooden ships using different kinds of metal fasteners. So don't mix your metals. Wood sickness is basically when a ferrous and iron fastener causes deterioration in a wooden member. What are other examples of that are more obscure? I'm not coming up with anything. The main thing that kills wood is being eaten by something else. So you can see that on either the micro or the macro level. But in any range of humidity or moisture between about 10% and about 90%, wood will rot, will decay, be eaten by bacteria, and especially in the southern, more southern parts of the ocean, more equatorial, I should say, parts of the ocean, you get a lot of creatures like worms and mollusks and whatnot, which will eat big chunks out of your ship, make their home there and drill in. Yeah, I'm not thinking of anything more obscure than that. Keith wanting to know about rake angle. Typically, American ships, 1800-ish, you're seeing 10 to 15 degrees of rake. Just about all sailing ships, you'll see some minimal 2 to 3 degrees of rake. And that's just a convenience. So all the lines coming from aloft don't end up in the same place on deck. All right. Well, if there are no more questions, I can let people free here, including Chuck, who has a small child nearby that probably needs attention. All right. So next week I'll know to go about 5-10 minutes longer with the slides, and hopefully we see you all again. Same bat time, same bat channel. Thanks, everybody.